Okay, so this is our e-learning for Wednesday, January 28th, and I have made a keynote presentation here. See if I can navigate through that. These will be the key takeaways or what we've learned so far this week about thermochemistry. So just to refresh a little bit, from physics, which you probably took a little bit of in 7th or 8th grade, probably 7th grade, we talk about what work is, the capacity, or what energy is the capacity or ability to do something useful. In physics, they define that as work, the ability to do work or capacity to do work. Work is done when a force acts over a certain distance. So work is force times distance and is measured in joules, or a joule is a Newton meter. And when force is applied to an object, it changes either speed or direction or both. And force equals mass times acceleration, measured in newtons, which a newton is a kilogram meter per second squared. And then all energy is measured in joules. Okay, not all energy, but energy is either measured in joules or calories. We're going to stick with joules for now because that's the International System unit. Internal energy. All objects have internal energy, which is symbolized by a U for some reason. It was the E boxes on the thing we did the other day. Increase in the internal energy usually increases the temperature. When it doesn't is when we're doing a phase change, and we'll see that later. Different objects at the same temperature may have different internal energies. There you can see in the iron and the brick, even though they're at the same temperature, they have different numbers of those little square E's. Same way with the water and the olive oil. Two samples of the same matter, the same size, have the same internal energy. I said has, but it should say have. Okay, so moving along. Also from 7th or 8th grade, we talked about solid, liquid, and gas quite a bit, and we talked about energy and motion and volume and shape. You may remember that. The solids are the lowest of the energy of the three. The particles are just vibrating in place. For liquid, they're in between intermediate energy. Particles can slide around each other. They're still touching, but they're moving around each other. And then for gas, the energy is high and the particles are free and independent. So as you increase the energy, you increase the motion of the particles, and eventually you get them to where they have enough energy to be free of one another. And that'd be a gas. Increasing the temperature will increase the speed of the particles. Changes of state occur when solid particles break loose from one another or liquid particles break free from one another, right, and become gas, essentially. And that's mostly a review of that earlier chart. Heat capacity is defined as the amount of heat energy required to raise the temperature of a sample of a substance by 1 degree Celsius. It changes depending on how large the sample is. And it's going to take a lot more heat to raise the temperature of 1 gallon of water than it will to raise the temperature of 1 cup of water. You might have noticed that if you've ever cooked and you're trying to make pasta or something and you put in too much water, it takes forever for the water to boil. If you take out some of the water, it'll boil quicker because it takes less energy. A gallon of water at 70 has more energy than a cup of water at 70 degrees. Specific heat capacity is the amount of heat energy required to raise the temperature of 1 gram of a substance by 1 degree Celsius. Now it's a gram, not the whole sample, just a gram. And specific heat does not change from sample to sample because it's always for 1 gram. If it's the same substance, 1 gram. Let's see, heat flow. Heat is the type of energy that flows between two objects due to a difference in temperatures. Heat always flows from the warmer object to the cooler object. Always. Warmer to colder. You can try this at home. Get a container of warm water, a container. Oops. What happened? What is happening? Okay. A container of very warm water, a container of very cool water, and a container of room temperature water. Put one hand in the warm, one hand in the cold for about a minute, then put them both in the room temperature. Your warm hand will think the water's cold, the cold hand will think the water's hot. Why? Because heat is flowing from the warm hand to the water, cooling the hand. Heat is flowing from the room temperature water to the cold hand, warming it up. So you got both hands in the same water, and it feels different to the two different hands. You're going to have big enough containers to fit your hands in. And don't use really hot, like boiling water or ice water or anything like that. Use just respectable water. Specific heat capacity is an intensive property or a characteristic property. That's the old school way of doing it. It means that it's the same for every sample of the material, no matter how big or where it came from. And there are tables of specific heats in textbooks and on the internet. When you calculate heat flow, we use the equation Q equals MC delta T. That was Tuesday's assignment. We were using that. Where Q is the heat flow measured in joules or kilojoules, M is the mass in grams, C is specific heat capacity in joules per gram degrees Celsius, and delta T is the change in temperature. Final minus initial. Notice that Q can be either positive or negative based on the direction of the temperature change. Warming up, Q is greater than 0, that's positive. Going down, Q is less than 0, that's negative. This is probably really boring for me to just read this whole thing to you. Changes of state or phase. When a solid changes to a liquid, the temperature does not change during the phase change. The energy is used to dislodge or separate particles from the places from its place in the solid. Because of that, Q equals MC delta T won't work because Q should be delta T, but it's not. Oh, Q should be increasing, but delta T is not, so that would be delta T is 0. In this case, a new concept, heat of fusion, replaces the C delta T part of the equation, and similarly, we use delta H map or vaporization when it's a liquid to a gas. And finally, when we think about phase changes, it helps to think in terms of heat flowing either into or out of the system. When a solid changes to a liquid, sorry, that question mark was an arrow before. When a solid changes to a liquid, heat must be added. Think of melting ice. Or when a liquid changes to a solid, heat must be removed. Think of making ice. If heat is added, it's called endothermic. If heat is removed, it's called exothermic. So if the system gains heat, that heat comes from outside of the system, and you and the thermometer are outside of the system. So what the thermometer will register a decrease in temperature, so it feels cold to you. I know that doesn't make sense. The system gaining heat, but the thermometer is not part of the system. So the heat has to go from the thermometer into the system, causing the temperature on the thermometer to go down. And if the system gives off or loses heat, that heat comes from inside the system and flows into the surroundings. You and the thermometer are part of the surroundings. The thermometer registers an increase in temperature. It feels warm to you. So that's kind of a nutshell. It's a big nutshell of what we've been doing this week. And I'm going to post for you a Quizlet that you can go through and just send me a note when you have finished both this video and the Quizlet. Thank you. Have a great day.